In this video I will show you how you can use the power law to dimension resistors in a circuit. And we will also look at 3 typical examples, and I will show you how to best approach such problems in practice. In the first example we will calculate the power from both current and voltage. In the second example both from voltage and resistor value, and in the third example we will compute the maximally allowed voltage at a resistor so that its power limit is not exceeded. And finally we will do an experiment in which you can see what happens if you intentionally exceed the power limit of a 15 ohm resistor by a factor of 20. Now the fire extinguisher here is already on standby. My name is Andreas from The Fearless Engineer, and here we go. In the last video we already looked at the performance law, which states that power equals voltage times current, and we combined it with Ohm's law. And if you don't know the video on Ohm's law yet, here is the link coming up for you. And what also might be interesting for you is the conversion circle at the end of the video, which you can easily use to find the correct solution formula for each task you will encounter in practice. But now let's have a look at the first task. And here you can see a resistor that is powered by a voltage source. And in the circuit here is a voltage meter that is placed parallel to the resistor and a current meter directly behind the voltage source. And the question now is, what amount of power is converted into heat at the resistor when the current meter indicates a current of 0.8 amps and the voltmeter measures a voltage drop of 12 volts. And the best would be to switch the video to pause now and to do the calculation for yourself before you watch the solution coming up. So switch to pause. And here's the solution coming up. And to solve the task we can simply use the power law in its original form, which states that power equals voltage times current. And if we use the numerical values, which are 0.8 amps and 12 volts in this case, we get to a power of 9.6 watts, which is converted into heat within the resistor. And this is already the solution to the first problem. And as I said before, the answer to the question of how to arrive at the original form of the power law in the first place and what energy and power have to do with it can be found in the last video. And what probably also has to be said about this circuit here is that a so-called accurate voltage measurement is performed here. This means that a voltage is measured with the voltmeter directly across the resistor and is therefore unbiased within the limits of accuracy of this voltmeter here. But the current meter is located directly behind the source and is therefore biased because the current flowing over the voltmeter is measured in addition to the current through the actual resistor. And this cannot be seen in the simulation here because the meters are assumed to be in perfect condition without any bias, but in practice every meter has a so-called internal resistance. And this means that in addition to the current through the resistor, a small amount of current, depending on the internal resistance of the meter, flows through the meter. And in a measurement this means that the calculated power will be a little bit too high depending on the ratio of the internal resistance of the meter and the resistance of the actual load. But in our case here the resistance is very small, it's only 15 ohms, and therefore we can neglect this error. In the second task we measure only the voltage across the resistor, thereby avoiding this problem of the potentially distorted current from the last example. And in order for this to work, however, we need to know the value of the resistor with sufficient accuracy, and we must also assume that it remains constant across all voltages and currents. Okay, here we go. By the way, the numerical values for the tasks are 12 volts for the voltage and 15 ohms for the resistor. And now is the time to switch to pause again so that you can work out the problem by yourself. So pause. And here comes the solution. As you have certainly noticed, we can't get anywhere with the power law alone because we don't know the current. So in order to be able to solve the problem here, we also need something else. In the last video I showed you how to combine the power law and Ohm's law, and we now need the version that contains power, voltage and resistance. And to get there we have to first rearrange Ohm's law by the current, so I equals U divided by R, and then we insert this into the power law and get to the form power equals voltage squared divided by resistance. And it's perhaps interesting to note that the voltage enters the power equation in a squared manner. This means that if we double the voltage, we get a quadrupling of the power. So if you increase the voltage on a component, the power and thus the heat generated also grows with a power of 2, and this can be quite a lot in some cases. And by the way, this is also what seals the fate of the resistor in our experiment at the end of this video. But now we want to insert the numerical values for the exercise, so voltage equals 12 volts and resistance equals 15 ohms, and with this we arrive at a power dissipation of 9.6 watts, just like in the first example. So now we also know how large the resistance actually was in the simulation, which we already took a look at. And this was already the second task. And by the way, almost 10 watts for a resistor is a lot of power. Most resistors are designed for a power of significantly less than 1 watt. And what happens when more power is consumed? This is what we will take a look at now. When you design a circuit, you have to make sure that the components in it don't get too much power and might be destroyed in the process. When you buy resistors, the label on the package usually indicates the maximum power they are designed for, and if you don't have the package, then you can at least estimate it from the size of the resistor housing. And on the photo here you can see different power ratings of various resistor types, ranging from 0.1 watts for the very small resistor up to 25 watts for the power resistor with a metal casing. And in this section we will now answer the question of how a resistor must be dimensioned so it doesn't overheat too much and gets destroyed in the process. A typical task could look like this, for example. A 100 ohm resistor with a quarter watt maximum power dissipation is to be integrated into a circuit. And the question is, what is the maximally permissible voltage drop at which the power limit is just barely not exceeded? I'll switch to pause again. We'll see you in a moment when you have solved the task for yourself. Okay, so let's take a look at the solution of the task here. We can combine the power law and Ohm's law again to get to the form P equals U squared divided by R. And we know the resistance value and also the maximum power from the problem definition, which means that we have to change the formula according to the voltage, which is voltage equals square root of power times resistance. And if we insert the numerical values, we get a maximum voltage drop of 5 volts, which is allowed to drop across the resistor before the power limit is actually exceeded. And such tasks naturally also exist for the maximum current, but for this purpose we must express the power law without the voltage in the form P equals I squared times R. Okay, and now it's time for an experiment. In the first task we have calculated the power which is converted into heat at the resistor from both current and voltage. And now we want to perform a measurement to determine power, which we do by connecting a voltage source with an integrated current meter to a 15 ohm resistor. And the upper value in the display shows the voltage that has been set and the lower value displays the current. And one useful thing here is that we can switch the voltage on and off with a push of a button here, which means that we can calmly wire everything first, and only when we are done with everything we can activate the source. And by the way, the lower value in the display when the source is not yet active indicates the maximally allowed current that the source will deliver at peak. And this way we can avoid that too much current flows through the circuit and components might get broken in the process. And atop the resistor, by the way, you can see a sensor that measures the temperature of the air directly above the housing. And the idea is to measure the temperature for each voltage level we set and see whether it rises in exactly the same nonlinear way as the power law predicts it. Okay, and here we go with the first voltage level. For this we set the voltage source to 1 volt and press start. And the current meter shows us a current of 0.066 amps. And if we look at the temperature at the resistor, we can see a slight increase of a little more than ½ degree centigrade. And the power consumption for the adjusted values, which we just set, is about 65 milliwatts according to the power law. And now we increase the voltage to a level of 2 volts and the current rises to about 135 milliamps, and the power converted into heat within the resistor is now at 273 milliwatts for the second measurement. And this means that the resistor has already reached its official design limit of a ¼ watt. But of course we'll continue to measure anyway, and you can see from the temperature gauge that the resistor has heated up to just above 32 degrees centigrade at the end of this measurement here. And at a level of 3 volts, the current rises to 200 milliamps and the power therefore amounts to 0.6 watts now, for more than double of the maximum value. And after a few seconds, we can see that the temperature has already risen to almost 50 degrees centigrade here. And we continue with a level of 4 volts in the next measurement and 275 milliamps, which heats up the resistor to over 70 degrees now. And then comes a level of 5 volts with 350 milliamps current, which leads to a power dissipation of 1.75 watts, which is 7 times the maximally allowable power for this resistor here. And at a level of 6 volts, the power is already over 2.5 watts with a temperature of over 140 degrees centigrade at the resistor, which slowly starts to affect its structure. And if you look closely, you can already see a slight discoloration here and some smoke rising up from the resistor housing. And we now continue with 7 volts, and with the current we are now already at ½ an amp of current, and from the smoke you can clearly see that the resistor doesn't feel very well at all now. This is also reflected by the temperature increase to almost 180 degrees centigrade now. And if we now increase the voltage level once more to 10 volts one last time, the resistor reaches its limit and burns out at a temperature of just below 400 degrees centigrade. So this was the experiment, and if we now take a look at the measurements in a few graphs, we can make several very interesting observations here. In the first graph, the resistance value is plotted over the voltage, and each point corresponds to one of the measurements we have conducted. And by the way, I used Ohm's law to calculate resistance, both from current and voltage, in the spreadsheet behind the graphic here. And what's certainly striking is that the resistance value is not constant, but decreases with increasing voltage. And up to the load limit of about 1/4 watt, this would probably not have been noticed very much, but because we pushed the resistor until it burned out, this effect is now nicely visible in the graph here. And by the way, this behavior occurs with many electronic components and is called positive differential resistance. And the counterpart is called negative differential resistance. And for our experiment here, this means that with increasing voltage, the current increases by a greater value than would be the case with a constant resistance value, which means that the resistor actually has accelerated its own demise by leading through a higher current at the end. And if we now take a look at the power curve, we can see here, we can easily spot that the power converted into heat at the resistor grows in a nonlinear fashion. And if we insert a regression function into the measured values, the point cloud here, and display the equation for it, then we can see that the growth is indeed quadratic. And this corresponds to our expectation based on the power law, because power is equal to the ratio of voltage squared and resistance. And by the way, the dark green curve you can see here shows the performance as it would be if the resistance would not change its value with increasing current. That is, without positive differential resistance. And the higher the voltage, the greater the deviation, and thus the additional heating as well. And since the resistance temperature is directly related to the power, the final thing we look at is the temperature curve. And the curve you can see here is almost identical to the power curve we just took a look at, and this is well to be expected because at the purely ohmic resistance, the kinetic energy of the electrons is converted into 100% of heat energy. So it's quite evident that the curve must look exactly like the power curve. But even if theory has predicted this, I still find it fascinating when such predictions are reflected in your own measurements. And for you, this means that in practice you can operate resistors above their power limit for a limited period of time without anything detrimental happening to them. But what we also have seen is that especially in the right part of the curve, a supposedly small voltage increase can have a big effect on the power dissipation within the resistor and thus also on the temperature increase, which is because the voltage enters the power equation quadratically. In this video I have shown you how to solve some typical tasks related to electrical power. You now know how to determine the power at a resistor from current and voltage. You also know how to combine the power law with Ohm's law if you only know voltage and resistance, and we also have determined the maximally allowable voltage at a resistor from its official power limit. And as always, if you have any questions or requests for topics I should cover here in my videos, just write me a comment down below and maybe I will make one of the next videos out of your idea. And if you like this video here, please consider subscribing to my channel because this will certainly keep me motivated to produce more such videos as this one here in the future. And finally, one last tip for you, you can download all my learning materials such as slides and circuit simulations and such from my website at thefearlessengineer.com. The link is coming up now in the banner. Okay, and that's it from me for now. Have fun and see you here next time on The Fearless Engineer.